Okay. Hello. In my talk, I will tell about what I'm currently doing for my PhD with my supervisors Yuri Klynishkan and Volodymyr Vovk. And my research lies at the intersection of more classical statistics with hypothesis testing and algorithmic information theory. So first I'll go through the basic notions, and then I'll describe the part of my research that's completely that can be fully understood just as a part of statistics, and then I'll tell how it's related to algorithmic information theory. So first, I'll briefly introduce p-values and e-values, or more precisely what I'll be talking about, p-variables and e-variables. So we are doing hypothesis testing, so we have some data X's, and we want to see if they can be described by some hypothesis H. So p-variable is just a statistic that takes small variables with low probability, and I think they are more famous and more well-known. And e-variable is some non-negative statistic that on average does not exceed 1. Okay, so why it's let's talk about why it's not that difficult to ask to switch from p-variables to e-variables. That's because this is quite easy to convert p-variable to e-variable and vice versa. From e-variable we can easily get a p-variable, and if we have a p-variable we can calibrate it, for example like this, and get an e-variable. So if we have statistic of one type, we can get a statistic of another kind. And e-variables exist. We always have some trivial e-variables, like any constant between 0 and 1. And for simple hypothesis, we have such a non-trivial example. So suppose we have density of our distribution and we have another subprobability density. Then we can simply consider the ratio as an e-variable. Well, if you integrate f, and f will just cancel out and you will integrate q. So e-variables and p-variables are more or less interchangeable. So why exactly would we like to study e-variables? And one possible answer is that they're quite nice to work with. For example, if we have independent batches of data, for example, gathered in different experiments, then we can gather all this data, gather all e-variables produced in the experiments, and just multiply them, and what we get would be another e-variable, which is nice. And well, assuming that we have some appropriate filtrations, we could talk about optional continuation that we can produce some e-value in one experiment and then decide if we want to continue and have our running product as an e-variable. And in case of dependent batches of data, we could also quite easily just take arithmetical mean, and this would obviously qualify as an e-variable. So e-variables make it very easy to work with data from multiple experiments. Okay, now let's talk about something more familiar, tests of randomness. As I see here on our conference, we mention Martin-Löf tests of randomness slightly more often, but my talk is focused on Levin tests of randomness, and it is essentially a lower semi-computable e-variable. Oh. There are some issues with how you defined the computation here, because we would also like sometimes to consider uncomputable distributions, which we assume are provided to us as Oracle, where we can request, for example, probability of a set with within provided error margin. And randomness deficiency is just an optimal test, which is great up to an additive constant than any other test of randomness. And we could also define information projection. So if randomness deficiency tells us how unlikely it is to obtain the data from distribution, then inf projection tells us how unlikely it is to obtain this data from any distribution of this kind. And I would briefly talk about a fact that was proven by Wolf, that we can define randomness deficiency for Bernoulli distribution and for exchangeable distribution, and also for binomial distribution. And essentially, if number of bits, number of ones in random string is is plausible, then it is as plausible to get the string from Bernoulli distribution as it is to get it from some exchangeable distribution. This fact by itself is not really important for our discussion. What's important is a step in the proof of this result. And it can be shown that in projection on the class of Bernoulli distribution can be approximated, well, essentially equals to this randomness deficiency relative to Bernoulli distribution with a certain parameter p hat, which is almost maximum likelihood estimation, but it's truncated, so we lose some data. How we compute it? We compute maximum likelihood estimation and find the nearest point of this net of dots. So essentially, for example, if we have 49 ones out of 100 bits, then we do not think that probability of getting 1 is 49 over 100. We think that it should be approximately 1/2 with some margin, because we cannot be sure. Okay, so my research comes from attempts to better understand this fact and generalize it. So we could talk about, we can consider some hypothesis, and which is composite hypothesis with many different distributions. And for each individual distribution inside this hypothesis, we have an e-variable for this corresponding simple hypothesis. And I claim that for many well-known distributions, for many well-known and natural distributions, we can interpolate these given e-variables to get e-variable for the big composite hypothesis, which basically takes this form. We somehow estimate the parameter theta and calculate e-variable for this estimated parameter. So far, we've managed to show this property, which I call e-variable interpolability for such distributions as binomial distribution, uniform distribution from 0 to n with variate n, Poisson, and normal distribution with one of the parameters fixed. So how do we prove this? The proof is very straightforward and mechanical. We just approximate one density with another and then estimate this fraction. So it's exponent of basically log likelihood. And and basically the proof is about using some basic information theory, classical information theory, to prove that we have a uniform upper bound. Well, so far, these results that I claimed, they're about single sample. I mean, sample of size 1, when we get some natural number, for example, and we try to understand if it looks Poisson to us. And of course, it would be interesting to study this question for arbitrary sample size. And here there less progress, but it's quite easy to show that you can prove something very similar for normal distribution with fixed variance. And I want to point out that here we should take denser and denser nets to which we round our estimation. And this is unavoidable. And we can, for example, consider a variable that's just 1 or something greater than 1 in small fixed neighborhood of, for example, 0.4. And then for normal distributions with the mean 0.4, this e variable, I mean, this complex e variable constructed from such e variable, this would be too large on average, and so we couldn't consider it as an e variable. So it's when we make estimation of the parameter, I guess it corresponds to our intuition quite well. When we have only sample of size 1, then we cannot claim much precision in our estimation. So there is no point in using a dense set. But the larger our sample is, the more information we have on what kind of distribution we work with. And so we need a denser net to represent our knowledge. Okay, so let's come back to algorithmic information theory and see how we can apply our results about e-variables to proven results similar to this one. Well, in the cases of all the distributions that we've mentioned so far, we can construct such lower semi-computable function C, which would be equal to our randomness deficiency on estimated parameter. So basically, what do? We ignore the distribution that is given to us. All the distributions that we've considered so far are computable, actually. So we can compute our distribution ourselves and use it as an oracle for the algorithm computing randomness deficiency. And well, with some with some corrections, we can avoid anomalous behavior on other distributions. Basically, we can do this by comparing the distribution that is given to us to distribution from our family, from our hypothesis. And the closer we get, the more we know about probability distribution, the more we're sure that it is from our family, the greater the greater the value that we return. So we can hold back our value that we computed until we know that we are from the distributions of our interest. So when we have this lower semi-computable function, we can first note that it should be at least equal to inf projection, simply by definition. But on the other hand, due to the results that we have for e-variables, you can see that 2 to the power of our function would be just some e-variable. 2 to the power of the efficiency would be an E variable, and so we could aggregate it, interpolate it, and claim that 2 to the power of our function is also an E variable. So we have lower semi-computable function that's an E variable, meaning that it is a Levin randomness test. So then we can apply optimality of randomness deficiency to prove that it should be at least equal to the test that we constructed. And thus we prove that our test is both greater than if projection of randomness deficiency and less than if projection of randomness deficiency, meaning that it is meaning that they're essentially equal up to some additive constant. So, and by noticing that E variables for uniform distribution could be used also as E variables for non-uniform distributions, we could also move from claims of this type to claims of this type, where plausibility for a number to come from Poisson distribution actually is the same thing as plausibility of the number coming from the uniform distribution on some appropriate segment. And well, that's basically everything that I want to talk about, and there are currently many related questions that I work on. So right now I'm mostly interested in understanding how much can we vary the nets, and what do these nets tell us about distributions that we study, and what these factors see from our definition. They're, well, I guess they're too bad for practice, but I've computed for Poisson, and it was just about around 22.2. So these are not some astronomical numbers, but something much closer to what we usually see in real life. And well, I'm still searching for a way to properly generalize the list of results that I've mentioned for different distributions, because essentially each time I use some properties of Kolbe-Kleibler divergence, and that the family of distributions is very nice, and it essentially lies on a curve that's very close to a straight line, as I understand it. And from this comes all the results. Here's just some reference for the facts that I mentioned at the beginning of my talk. And I guess that's it. Thank you for your attention.